Hello guys, welcome back to Maths on African Motives. Still working on our engineering science. We shall be focusing on the August 2023 exams that we actually wrote so that we can have a revision from this paper as we are having from our August 2023 exam, the X paper that we had. So we are going to quickly rush through the sections so that we properly see what you're given. Remember your information that you're given. So this was actually a request that was being asked from one of us. So it's important that we work with the question paper together so that we'll see how we're supposed to attempt these typical questions. And for those who will be preparing for the October, November exams there, you also have to play around with this part because they ask in similar ways actually. So the first part was on dynamics, that is 1.1, define the following quantities and give the SI unit. Take note, we are asked not just to define, but also to give the SI unit for each, all right? So we have got the displacement, the first part whereby we know that displacement is the straight line distance that a body moves that is measured in meters. So here we are simply referring to say is the straight line. All right, so we are having the straight line distance, distance that a body moves. So we are talking about a body applying to a certain distance that a body moves. All right. Measured in meters. So the SI unit there, we are talking about this measured in what? Measured in meters. All right, so that is the idea of our displacement. All right, we are talking about the straight line distance. Remember, if we are talking about distance, you'll be referring to the condition whereby we are talking about the one that is being moved throughout. All right, if we are talking about this in form of, let's say, this is how the object was moving, starting from point A, all right, to point B, to point C, to point C here, to point D, to point E, up to point F. So if we are referring to an object moving from point A, B up to F, this is the distance that being traveled: A, B, B, C, C, D, D to E, from E to F. We are referring to the distance, but the displacement is the one that we are taking from A to F direct. That is our displacement in this case. All right, so that is the idea. So let us see the other part of our question, which is the speed. So speed is just the rate of change of distance. Speed from distance. Velocity is from displacement. So velocity is the rate of change of the displacement, but the speed is the rate of change of distance. So this one is the rate of change of distance, the rate of change of distance. All right, so that is the idea of speed. All right, measured in what? Measured in meters per second, or you can write this as meters per second like this. So that is the idea that you're going to have. Then we've got the weight, which is also can be asked or posed with the what? With the mass. They can ask just like what I was explaining: speed, velocity, distance, displacement, weight, mass. So you are supposed to know the difference of each. So the weight is simply the gravitational force. All right. So this one is the gravitational force acting on a body. So that is going to be our force in this case. All right, so remember, we are simply referring to the weight being the product of mass times the gravitational acceleration. So this one is now measured in what? In newtons in this case, all right? So this one is measured in newtons. So that is what you're going to have for the first part. You've got 6 marks for that. So make sure that you answer the question properly. Like this part here, they wanted not you to define, but also to state SI unit of what? Of the given part. All right, then 1.2, you're given an information that the following data refers to a vehicle which moves from rest. Take note, this vehicle is moving from rest on a horizontal plane in a straight line. So meaning to say, if it is moving in a straight line, we are going to end up having a relationship of velocity with respect to time in a straight line, depending with how the object is moving. All right. So in this case, we are given the constant acceleration of the vehicle and also the duration of motion, which is the time. So duration of motion, we're talking about time measured in what? In seconds. So the first part of our question was 1.12. Calculate the displacement after the first 3 seconds. All right, let us take our data first before we talk about the question. This object is starting from rest. From rest, it means our initial velocity there is at 0. That is from rest. We are given the initial velocity there, which is 0 meters per second. That is from rest. So we are starting from this part. Then it moves and we are given there the acceleration, which is a constant of what? Of 5 meters per square second. Meaning to say, if it is maintaining a constant acceleration, we are going to have our object in this manner, starting from rest, maintaining the constant acceleration. That is, in this case, remember, you'll be having your time, and here you'll be having your what? Your velocity. So that is the idea. And we are given the duration for that particular moment where we are given this as what? As 4 seconds. From this information that we have, our question is to calculate the displacement after the first 3 seconds. This information is for the 4 seconds, but we need after 3 seconds. If you are going to work it from the diagram, I'm going to explain 2 ways that we could have worked this type of equation here. Take note, we want to calculate the displacement. So we could have used our formulas from our linear motion. Remember, from our linear motion, we've got S is equal to UT plus half AT squared, whereby we are talking about what? The displacement. We have a formula, V squared is equal to U squared plus 2AS. So there are actually many formulas that we have here. Let me just try to list them. U squared plus 2AS. We also have V is equal to U plus AT. These are some of the formulas that we actually can use into consideration, and also the one for the average velocity, U plus V over 2 times what? Times T, for the average velocity that is being what? That is being taken. These are some of the things that we can play around with from our linear motion. So in this case, we are given to calculate the displacement. So we can use this formula, given that the time, take note, the time is not at 4 seconds, but the time is at 3 seconds, meaning to say we are considering our time this time as 3 seconds on this part. Our T is supposed to be 3. So we can substitute our information, the one that we are given. So meaning to say our S in this case is going to be UT, that is our U being 0 and our time being 4. So that's 0 times 4 plus half of AT squared. We have the acceleration in this case, which is 5 times time. The time now that we are using is the one that we are given in 3 seconds. So it's going to be T squared, which is 3 squared in this case, from the time that we are given, not the one that we are given in the first place. No. So from our calculator here, let's see what we are going to have. So like I said, I'm going to explain another way. So 0 times 4 here, guys, that's a 0. Yes, you can just use your calculator, but this one, you know, that's a 0 there, plus half of 5. So you're going to have half of 5 times 3 squared in this case. So that is 3 squared like this, which is going to give us 22.5 meters in this case. So we are going to have our S as 22.5 in meters. So that is the whole idea of our question. We are going to have our displacement from the, like I was saying, we could have applied like the idea of our diagram here. Let me explain from this diagram. Like if you wanted to work from your diagram, let's say wanted to work from this diagram. We understand that from this diagram, this is our time, whereby this is at 0. We go 1, 2, 3, 4, 5, and so on and so on, corresponding to the velocities that are going to be here. So if you were to take note here, we were given the acceleration, which is of what? 5 meters per square second. Knowing that we started at 0, it's a constant acceleration. So meaning to say these times are going to correspond at 4 here. We are going to have a corresponding velocity that we do not know in this case. The same thing at 3 here. We are going to have a corresponding velocity that we do not know. So if you wanted to use your diagram, you know that the displacement they are referring to is simply the area under the graph that is being traveled in the first 3 seconds, meaning to say we're supposed to calculate area of this section under the graph. Remember, under the graph. So we're considering for the first 3 seconds. But in order for us to calculate the area, we're going to need from this point up to this point, which is 3 units. 3 minus 0, which is what? Which is 3. So here for 3 units. But we do not know now from this point up to this point, we do not know this velocity here. So meaning to say you were now forced to calculate this velocity at this point. From which idea? From the acceleration concept. Because we know that acceleration is the change of what? Change of velocity. So from this part, if we know that acceleration is the change in velocity over the change in time, we are simply going to substitute our information and calculate that velocity, because we are saying we have the acceleration, in this case of 5, which is equal to the change in velocity, that is the velocity at this point, the one that we want to calculate, corresponding at 3, the one that we do not know, minus the initial. The change in velocity simply means V2 minus V1, final minus initial. So the V1 is our starting point at 0 in this case. Everything over the time that was taken. Now we are considering, remember, our displacement in the first 3 seconds. So in this case, we can calculate the value of V minus 0, that's a V. So you're going to have 5 is equal to V over 3. So you can cross multiply to calculate the value of V. We're back to our mathematics. 1 times V, that will be V 3 by 5, which is going to be 15. So meaning to say, at a velocity, at a time of 3 seconds this time, the velocity corresponding there is 15 meters per second. So meaning to say we know now the value at this point that it's 15. If we know the value here, we are now back to the statement that I was saying. Displacement is the area under the graph. So we are going to take the area taken from this triangle, which is a right-angled triangle in this case. So meaning to say our S was going to be considered as the area under the graph. All right, we are going to consider this as area under the graph. All right, so let me have this way. So meaning the shape that we are considering here is a triangle, this shape here. So we are considering the area of a triangle. So meaning to say our S was going to be half base times the perpendicular height, which is half of the base from 0 up to 3. That is our time in this case, which is 3 times the height from this point up to this point, which is the one that is corresponding at what? At 15. So this whole part is supposed to give us the displacement. That is the whole idea of our question. Let us check from our calculator if we are going to have the same answer. That is going to be half of, so you said half of 3 times 15. All right, so we've got half of 3 times 15 in this case, like this. So as we can see, we are obtaining 22,5, which is the same answer as the one that we got from our previous section, or from our previous solution that we obtained from our calculations here of the formulas for linear motion, whereby here it's a direct, or it's a straightforward calculation that you're simply taking because you have these formulas. So you simply have to substitute. All right, so that was the whole idea of this question. But if you are to check now, they're asking on 1.22 to calculate the velocity after 4 seconds. Now we need the velocity after 4 seconds, which is 2 Mach. So as you can see, we can use the same idea like what we did here to calculate the velocity from the diagram concept, to calculate the velocity after 3 seconds, meaning to say after 4 seconds, we are simply going to substitute a 3 here, a 4 here. So it was going to be a 4 here, 4 times 5, which was going to be 20 meters per second. But we could also have used our formulas in this case. Remember, we've got our formulas here that for linear motion. So this one can actually work properly. So meaning to say our velocity, which is final velocity, is given as u plus at, which is the initial velocity times plus acceleration times our time. So in this case, we need the final velocity given after 4 seconds. So you're taking this whole information as it is, but this information is corresponding at 4 seconds. So meaning to say our u there is a 0 plus at, that is acceleration times the time. So you're going to have 5 multiplied to 4. So this one was going to give us our velocity. Here, if you multiply, it's going to be 0 plus 20. Which is going to give us 20 meters per second. All right, so that's velocity. Remember, also the units of measurement. So as you can see, we are obtaining the same answer, even if we try to use that diagram concept that we used before. It was going to work, but the best there was just to use your formula. All right, then now we want the time to reach a velocity of 15 meters per second. So this time they gave us the value of v, the final velocity. What we need there is the time that is going to correspond at this velocity of 15 meters per second. So what does it mean? We simply go back to our formulas. In this case, we saw that this formula can give us velocity at the same time with time. So we can play around with this formula. That is going to be v is equal to u plus at, whereby in this case, if we are to check, we are given that our time, the velocity at this moment is at 15 meters per second. And the question there is asking us to calculate the time. So meaning to say we are just substituting our information we are given that velocity, final velocity is supposed to be 15. The initial velocity is not changing. Our object started at 0. This is where the object started at 0. So meaning to say this one is not going to change. We are going to have 0 plus. Our acceleration also is not going to change. Our acceleration is a constant. It's a constant acceleration. We maintained a constant acceleration of what? 5 meters per second throughout the movement. So it's going to be 5 times t. So that means we can calculate the value of t from there. So 15 is equal to 0 plus 5t, which is 5t. To find t, we can simply divide by 5 there. So t was going to give us 3 seconds. Remember, time is measured in seconds. So our time then was going to give us 3 seconds. All right, so that was the whole idea of our question. Then if you check on 1.24 now, they wanted us to draw a velocity time graph for the movement of the vehicle mentioned in question 1.2 and show all the important values calculated above. So we need the velocity time graph in this case. From this information, remember, we listed our information. In this case, we have our information from this part, and like I said, from this part I actually explained a sketch of how your velocity time graph is supposed to be like from our time in seconds, our velocity, but we are supposed to have this now according to scale. We are supposed to have this graph according to scale. We are supposed to draw it properly according to scale, having all your points indicated. In this case, we are going to indicate all the points that are from this point, all right, from your graph. All right, we have 3 versus 15 is your velocity in meters per second, your time in seconds here. So we said we've got 3 versus 15, that is important. Then 4 and its corresponding velocity. If you check here, we calculated the velocity at 4. At 4 here, if I'm not mistaken. Yes, here we calculated the velocity when our t was 4 in this case. Our velocity there was 20. So meaning to say 4 on our graph is going to correspond with what? With 20 in this case. So this 4 was supposed to be corresponding with the 20 on this side. All right, so these were the most important points for you to show. So this line here representing our acceleration, which is what? Which is 5 meters per square second. That was the whole idea. So I want you to draw this part on your graph properly according to scale. And you draw this according to scale, but as you can see, it's just a normal straight line graph that we are used to. So that is our 1.24 in this case to draw the graph and showing the points that were necessary there. That was going to be 3 marks. All right, so as you can see, 15 marks for everything. All right, let us check the question 2 now, whereby we are given the part of statistics. All right, statics, sorry, I'm now thinking of our mathematics. So we have got the statics part, whereby now we are given 2.1, name 2 methods that can be used to solve parallelogram of forces. Okay, here we're supposed to not be parallelogram of forces, because parallelogram of forces, like we are talking already of a method that we are using. We are just talking about method that we use to solve when we are given a lot of forces in this case. All right, we are given many forces, but we want to combine them into a single force. So we are saying, which methods can we apply in solving this part? Which methods can we use? All right, so we have the parallelogram law, which is actually taken from our analytical. All right, so we've got the parallelogram law, which is actually taken from our analytical method. In this case, we are simply referring to our analytical method. All right, we also have the triangle law. So we've got the triangle law in this case, which is referred from our graphical method in this case, all right, which is taken from our graphical method. All right, so that is the whole idea of our question. Then 2.2, we are given this part here. They wanted us to understand our forces, because you are given an unknown force. We do not know this force, but it's inclined at 25 degrees to the horizontal. Then we are given the horizontal component of that force. Remember, we have got a condition like this. This is our horizontal part, and we've got an incline at an angle of 25 degrees in this case, like this. So we have got a certain force that is being applied, and we do not know this force, which is the unknown force at this point. But we are given now that the horizontal component, which is the force that is going to correspond in the horizontal, remember you've got a 90 degrees, and this is the horizontal, which you can take it as Fx, or you can take it as what? As Hc for the horizontal component. And we also have the vertical component in this case. We know that horizontal components carry the cosine of theta. We have this value for the horizontal component, which is 950. This is the one that we are given as 950 Newton. So the question is to determine the value of the unknown force, which is this one. You are simply going to ask yourself, how are you supposed to determine this horizontal component in the first place? Remember, the horizontal component is given as what? As the force that you be having here, cos of theta. If you are talking about the vertical component, is the force that you are going to be having here, the sine of what? The sine of theta. So meaning to say, from our formula alone, this was going to help us from our formula alone understanding this, because we know that this horizontal component of 950 Newton was taken from F cos theta. So we are going to have this as F cosine of theta, which is the angle of incline of what? Of 25 degrees. Which is, we have formulated an equation from there. If you were given a vertical component, you're going to use the one for the vertical component. VC is equal to F sine theta. But in this case, we are given a horizontal component. So we have to work with this formula for what? For the horizontal component, which can be given as Fx for the horizontal. All right. So here we're just substituting into the formula. Then we can calculate F by making F the subject, divide by cos 25 both sides. Since we are multiplying here, we can divide by what? By cos 25 since we are multiplying. So we're going to divide by cos 25 both sides. So that is going to give us F. So our F in this case is going to be 950 divided by cos 25, which we can just have from our calculator in this case. All right, so let's try to have it from our calculator and see how it was going to be like. All right, so this is what you're going to have from our calculator. That's make sure that your calculator is in degrees. There's a D there. Make sure that you have a D on that part to show that you are in degrees. All right, so that's 950 divided to cos 25, close your bracket there. All right, so that was going to be 1048,209 and so forth, which is 209 in this case. So that's 1048,209. All right, 1048,209 in Newton. This the other force that we are given, it's in Newton. So meaning to say our answer also is supposed to be in what? In Newton. If you were given kilonewton, then this answer also supposed to be in kilonewton. But if you want to express your final answer to kilonewton at the end, it's fine. You can do that, but there was no need for us to do that. All right, let's check now the other part. We were given, in this case, a horizontal beam resting on two supports, L and R, is shown below. So this is what we have from our information. We've got the support here at L and the support at R in this case. All right, then we have got 4,5 meters in between points here. Let's try to have this 4,5 between these points. All right, then here 1 meter up to this point here, there's 1 meter from this point to this point, 1 meter from this point, 2 meters, 80, 40, and 35. So from this information, what does it mean? Let us consider from this point here, from this point up to the end. We want to know what is happening here. The whole distance from this point up to the end here is 4,5. So meaning to say we can be able to determine the remaining distance here before we attempt our question up to the end, because we know that from this point up to this point is 4,5. So we're going to subtract this here from this point, which is we are going to subtract this 1 and this 2 from what? From 4,5. So that is going to be what at the end? Let's see. That is going to be 1,5. That's so. We are saying 4,5. That is 4,5. This one. We subtract these two, 1 and 2 in this case. We are going to subtract 1 and we also subtract a 2 in this case. So that was going to be 1,5. So meaning to say at the end here, we have 1,5 meters in between. So it was important for you to have your diagram completed so that when you are calculating whatever that you're calculating, your diagram is there with the everything information that is required. So our question was to determine the reactions of both supports by taking moments about each support. So you're supposed to take moments about L, we take moments about R, about each support that we are given in this case. That is the question, about each support. All right, so let us consider the first part. All right, let's just try to have it on this part, or you can just try to decrease it and have it on this part here. So let us consider to say, if we wanted to take L, if we wanted to start with moments about L, taking moments about L in this case, all right? So this was 2.3, all right? Taking moments about L. Taking moments about the point L, all right? Considering what is happening from our movement, in this case, R back to L, if we check our R now, going to L, because we are taking to L, meaning to say R is going in an anti-clockwise direction. The movement that is taking, it's anti-clockwise. Remember, this way, that is anti-clockwise, and this way is how the clock moves. This is what? The clockwise. So in this case, we are given a consideration as this R is going this side, it's going in an anti-clockwise manner. So meaning to say we can refer to the sum of the anti-clockwise moments being equal to the sum of the clockwise moments. Here the formula, you can start with this side or this side. As for me, it's best to start with the side of the one that I'm calculating, but it's just one and the same part, all right? So here that means R is going in anti-clockwise, but we need the sum of everything that is going in anti-clockwise back to L. So let us have force times distance, which is R times the distance back to L. What is the distance there? 4,5. So it is going to be R times 4,5 in this case, like this. We check for any other part that is moving in an anti-clockwise back to L. All right, if we check this one, it's moving this way, which is clockwise. This is where the clock is moving. If we check this one, it's moving in a clockwise. But if we check this 8, it's moving this way, which is anti-clockwise. Check the direction. So meaning to say the 80 that we have, it's in the anti-clockwise. So we are going to add it on the anti-clockwise. We are going to add force times distance. That is 80 times the distance from 80 back to L. We have got a distance of what? Of 1 meter there. So we're going to multiply by 1. All right. So that is all we have in the anti-clockwise. And the rest, as we saw, this one is clockwise. This one is clockwise. We're going to add them together on the clockwise. That is sum of, we add them, the moments that you're going to have. So let's start with the first one of 40. So 40 here, as it is going to L, the distance between 40 and L is what? It's 1 meter there. So it's going to be 40 times 1. All right, that's force times the distance. Plus, we move on to 35. As 35 is moving back to L in the clockwise, what is the distance between these 2 points back to L? So we simply add from here, which is 2, up to here, 2 plus 1, which is 3. So it's going to be 35 times 3. So you have to consider your distance in this case. All right, so as you can see, after this, we can simply combine R times 4,5. It is going to be 4,5 R plus 80 times 1, which is 80, which is going to be here. You just combine everything on the other side. You can just combine everything. Let's just see from our calculator here. If we combine, that's 40 by 1. We add 35 times 3 in this case. All right, so this is going to be 35 multiplied to 3. All right, so that's 145 at the end in this case. All right, so here we are going to obtain 145. So if we are to find R here, we can transpose the 80 to this side, meaning to say, if we transpose 80 to the other hand here, it is going to be a negative. In this case, it was a plus. So on this side, we are going to subtract the 80. So on our calculator from 145, simply subtract 80. In this case, we've got 65. So meaning to say, we are going to have 4R being equal to what? Being equal to 65 in this case. All right, so to find R, simply divide by 4,5 both sides. Since you are multiplying, you can simply divide by 4,5 both sides. So that was going to give us 14,4444 and so on and so on and so on. That is to 3 decimal places is going to be 14,444. That other part is not going to change. Measured in what? In newtons. As we can see, the other part that we are given is given in what? In newtons. If they were kilonewtons, then you have to express your answer in kilonewtons. But in this case, we are dealing with what? With newtons in this case. All right. So this was obtained by taking our moments about L. So with the same idea, we can take our moments about R. So taking moments about R in this case, what is going to happen this time? So this consideration here is going to change. This part here, the movement is going to change because we are considering about R. So let us start with the side of L. How is L moving back to R? This is our L back to R. So as you can see, it's going in the clockwise. This is how the clock is moving. So this one is going in the clockwise direction. All right. So meaning to say we can consider the sum of what? The sum of clockwise moments equal to the sum of the anti-clockwise moments. If you use the same formula, anti-clockwise equal to, you still get one and the same thing, but it's just best for you to work with the unknown part that you are working with and on the side, on the left-hand side, so that you can properly work, but does not even affect our calculations at all right? So here we are going to have the clockwise, that is L back to R here. What is the distance between? So that is going to be L times the distance back to R here. It's 4,5. All right, is there any other force that is referred to R here, back to R, that is going in the clockwise? If we check, we're supposed to have these forces on this side. These are the ones that we're going to be moving in the what? In the clockwise, but we do not have anything on the right side of R. All these forces that are remaining are moving in the anti-clockwise, which are on the left side. These forces back to R here, they are going in this way, opposing how the clock moves. So meaning to say the rest are going to be referred on the anti-clockwise in this case. All right, so for the first one, let us start with 35. 35 back to R here, there's a distance of 1,5, the one that we calculated before. So this one is going to be 35 times 1,5, which was the same thing that you're supposed to do from the 40 back to R. In this case, what is the distance? We've got 2 plus this 1,5. The 1,5 is also involved in this case, so it's going to be 3,5. All right, so this one, we are involving this 1,5. So at the end, it is going to be a 3,5. So like I said, we are going to have plus 40 times 3,5. All right, we move on to the 80. So 80 back to this one, we have to add, but here we can just add because already we know that from this point up to this point at the end, it's 4,5. So you simply add this 4,5 and the one that is from L to the other side, this one here. So if we add this 4,5 and this one, we've got the whole of the line, which is going to give us what? 5,5 in this case. All right, so meaning to say we were supposed to have this as 5,5. All right, so that's plus 80 times 5,5. All right, so that was the idea of our question like this. So meaning to say here, we just need to combine and calculate the value of L, which is the unknown in this case. All right, so if you multiply L times 4,5, you're going to obtain 4,5 L is equal to, you combine everything on the right hand side. In this case, from your calculator, you can just have this quickly combined. Let's see what you're going to have, which was going to be 35 multiplied to 1,5 in this case, plus 40 multiplied to 3,5. All right, plus we move on to 80 by 5,5. So that was 80 by 5,5 in this case. All right, so this is going to give us something like 632,5. So we have got 632,5 divide by 4,5 by 4,5, so that we obtain the value of L. So if we divide by 4,5 in this case, this was going to give us what? 140,555 and so on, which is the 5 is going to change this one into a 6. So you're going to obtain 140,556 in Newton in this case. All right, so that is the whole idea of our question. So in actual sense, what it simply means, you can just prove this on your calculator. Yes, you can even write it down because you're not even asked to prove this, but as we know that the sum of the upward forces should be equal to the sum of the downward forces. So the sum of the upward, you're talking about the L and the R, the ones that are facing up. These are the upward forces, the ones that are pointing up. So meaning to say, if we are to add these two forces, the L and the R, all right, if we are to combine this from our calculator, this one, you're not asked about it, so you can just use our calculator direct, because you're not even asked about to prove our answer, but it's important just for you to check. Okay, so let's see from our calculator. Remember, we're saying upward forces, it's L and R. So we're going to add our L here, which is 140,556 plus 14,44 in this case. This was going to give us 155. So you're going to obtain 155 Newton for the upward forces. You do the same thing for the downward forces, the ones that are facing down. In this case, these are our downward forces. We've got 80, we've got 40, we've got 35. So what are you going to obtain from these forces if we are to combine them? All right, so you said we've got 80 plus the 40 there, plus the 35 in this case. All right, so this was also going to give us 155, which is the same as the one that we obtained in this case, 155 Newton. So that is a case for you to have, because remember you calculated from different, you were taking moments from different points. So having these answers the same is supposed to be a guarantee for you to say that you have everything in the correct manner. All right, so let's check another part. So that was actual 10 marks for our question 2. All right, let's check the energy and momentum in this case. On question 3.1, we're asked now to define the term momentum in this case. All right, so here's just a definition. Remember, momentum is taken from the product of what? Mass and velocity. So here we are simply referring to say is the quantity. This one is the quantity that a body possesses. So this is the quantity that a body possesses as a result of its motion. So that is what we have on the momentum there, whereby we are referring to the momentum as the product of mass times what? Mass times velocity in this case. So that was our definition, straightforward. Then we are given in 3.2, a brick falls freely from rest. So we have got a brick that is at a certain point and it is falling freely from rest. Let's say from a certain point is falling down, given a certain height, in this case falling from 19 meters to the ground. So given the kinetic energy of 1.75, so this was 1.75 kilojoules in this case, which was the kinetic energy. All right, so the question is to calculate 3.1, the velocity of the brick just before it hits the ground. All right, so let us just see from our information. That was 3.2. So like I was explaining from this part, to say we've got our object that is falling down to a certain height in this case, which we are given the height there, which is our height. Remember, it's just represent the displacement, but it's the height, the distance, the height of 19 meters that you can write as S is equal to. So someone can use S in place of the height. It's just one and the same thing. Then also we are given the kinetic energy in this case. Remember, the kinetic energy we are given is 1.75 kilojoules. That is the only information that we have. So I want us to take this information back here. The question is to calculate the velocity of the brick just before it hits the ground. All right. If we are to consider, this information is limited, because as we understand that the kinetic energy is supposed to be taken from half mv squared. This is what we know, half mv squared. But since here we do not have the mass of the, and we are even asked to calculate the mass later on, there's something that we understand about this energy concept, to say the kinetic energy, or in terms of energy, remember that is not lost from the law of the conservation of energy. Whenever you are conserving energy, you are going to say that the value that you are going to have for the kinetic energy is going to be the same value as the one that you are going to have at the end for the what? For the potential energy. The potential energy taken to kinetic energy, a reverse. So knowing that, we can take it as an advantage, because we are simply saying our kinetic energy at the end is going to be equivalent to the potential energy that was being stored before. Remember, this potential energy is the one that is being stored. So from our kinetic energy, we have half mv squared from our formula. we want to formulate the formula that is going to give us the velocity in this case. So half mv squared, of which you're supposed to know the formula. Then for the potential energy, you know that it's mgh. So we want to find v here, which is our velocity, remember. So we want to formulate a formula for v. Since m and m is common, we can divide by m here. This one cancels. To remove these two, a half, we can multiply by 2, we can multiply by 2 both sides. So meaning to say, we are going to remain with v squared equal to 2 times gh. So to find the v, we introduce the square root both sides. So v is equal to square root of 2gh in this case, which can be given, like I said, h can be given as s. So you can write this formula as v is equal to the square root of 2gs, where here we are talking about the displacement, the distance that was taken. So as you can see, this formula here, you are supposed to know it, but here was formulating where it was actually taken from. But our question here, you were supposed to actually have your formula already. All right, so meaning to say, in this case, I'm going to use this formula that V is equal to the square root of 2GH, whereby I'm given, remember G, from our information, that's 9.8. So it's going to be 2 times 9.8. Our gravitational acceleration, we have this value. Then the height, which it fell from, is 19 meters in this case. So we're going to multiply by 19. All right, so this was going to give us our velocity of 19.298 in meters per second. All right, also just use your calculator direct. We are going to obtain this value. All right, so that is how they sometimes want us to play around with our formulas, connecting the kinetic energy and the potential energy to formulate the formula for V, but you are supposed to actually know your formula under exam conditions. You can see 2 marks and you want to formulate this formula and so forth. So 3.22, you are now asked to calculate the mass of the brick. So now we have the velocity. So we can go back to our formula for the kinetic energy. Remember, we said the formula for the kinetic energy, it carries the mass. So we can use this formula now since we have the velocity. All right. So meaning from our formula that kinetic energy is equal to half mv squared. We can simply substitute our values in this case, or we can make v the subject depending with what, we can make m the subject. Remember, we want to calculate mass. So you can make it the subject, or you can just substitute your information in this case, whereby we have got AK, our kinetic energy, 1.73 kilojoules. So remember, kilo, that's times 10 to the exponent of 3. All right. So meaning to say here, we are going to have 1.75 times 10 to the exponent of 3 equal to the half of mv squared. So you're going to have of m times the v squared, which is 19.298, but everything is being squared in this case. So it's up to you how you're going to solve. Maybe you're going to multiply this direct, or you can remove this part by multiplying by 2, whatever part that you're going, or you can simply divide by this part on the other side, because what you want here is to remain with this m. So our m at the end is going to be what? From our calculator, we can simply divide here. Let me show you on the calculator what you could have done straight. Just have a fraction. Remember, we want to remove this side, so we divide on 1.75. So it's 1.75 times 10 to the exponent of 3. Then we simply divide by everything by half of. So we're going to divide by half multiplied to this bracket, which is 19.298 squared, like this. All right. So it's just one and the same thing, because what we just want is to remove the half and the 19.298, which is being squared on this side. So the moment we divide, we are obtaining 9.398, which is our mass. So our mass is going to be 9.398. Remember, our mass is being measured in what? In kilograms in this case. So that was how we're going to obtain this mass from the given information that we have from our kinetic energy. Then the potential energy of the brick when it is covered 12 meters from rest. Remember, this object is falling from rest. It's supposed to fall for 19 meters. So in this case, as it is falling from rest, they are saying it did not cover now the exact 19 meters. It is just covered 12 meters. As it is falling, it is covered 12 meters, meaning to say it is not reaching the ground. It's supposed to reach the ground to cover the 19 meters, but now it is not because of what? The 12 meters that we are going to have. So how are you going to calculate the potential energy? We are going to simply have the difference, that is the one, the potential energy, the energy that is being possessed and due to the body. So we are going to subtract the differences of the heights in this case. Remember, the whole height was 19 before. So you subtract, you get the difference between this point. This is where you are going to, this is the part that you're going to remain with in that case, all right? So meaning to say our part here is going to be given as potential energy, that's 3.23. Remember, our potential energy is given as mgh. So this time we have our mass, which is 9,398 times the gravitational acceleration of 9,8 times. But on the h now, we are going to subtract the difference between. So remember, our actual height is supposed to be what? 19. But now we have covered 12 meters. So it's going to be 19 minus 12 in this case, all right? So this is just going to be 19 minus 12. So that's it. We have you have got your potential energy in this case, which was going to give you something like 644,703. Remember, we are now talking of energy in this case. So energy is supposed to be measured in what? Supposed to be measured in joules. All right, so that is how we could have played around with this information. As you can see, it's just 7 marks for that, everything. So it's good to know your formulas and how to apply your formulas as well. 4.1, we are given to define the term power. Just 1 mark is this. You know that power is simply the rate of change of what? The rate of doing work. So not the rate of change, but the rate of doing work. So this one is the rate of doing work. Just like that. All right. The rate of doing work in this case, which is measured in what? In watts, which is the joule per second, which is referred to as a watt. All right. Then we are given a cable with a, wait, take note here, we are not talking about something that yes, got wait, it's the cable. This is the weight of the cable actually. So we're given the cable of a weight being 525 Newton is lifted and wound onto a drum 35 meters above the ground, meaning to say we've got a condition. If we are dealing with a cable, this is what we are going to have at the end from our force distance graph, all right, whereby here we are going to have our distance on this side. So this is where we have our distance, and this is where we have our what? Our force. So here, this is the force of 525 over a distance of what? Of 35 meters. That is what we are given in this case. If you are dealing with what? If you are dealing with the weight of a cable itself, all right? So the question was on 4.1 to calculate the weight of the cable per meter length. We already have the weight of the cable 525 and the distance that was wound. So meaning to say, we are simply going to divide the weight that we are given of 525 to the distance that is being what? Taken of 35 meters in this case. So this one is going to give us the Newton per meter. So we are going to obtain 15 Newton per meter in this case. So that was the whole idea of this part, all right, to say already we have got the weight of the cable, right? So to find the weight of the cable per meter length, we are simply dividing by what? By the meters that were being wound on the drum. All right, on 4.22, we are now asked the work done in winding the total length when the total length is being wound on of the cable onto the drum. What is going to be the work done? So now we can refer to this as the area. Remember, our work done can be simply taken from what? From the area under the graph, or we can take our work done from the average force times what? Times the distance in this case, all right? So we've got two formulas that we can consider here. We can use the condition of the area, like we have like a graphical presentation like this. So it is going to be the work done is going to be given from area in this case, which is the area of a right angle. This is a triangle, so you're going to use area of a right angle triangle of PH, all right, which is going to be at the end, we are going to have half times the base from this point up to this point. That's our base, which is 35, times the height in this case, which is what? 525 in this case. So that will be 525. So we are going to obtain 525 in this case, all right? So that was going to give us the work done from the area. Like I said, we could have used average velocity. I'm going to work that one again. Let's see this one first. So it's going to be half of 35 times 525 in this case, all right? So this is going to give us 9187.5, all right? So we are going to have 9187.5. This is work done, which is being measured in what? In joules in this case, or you can express in kilojoules if you want, right? But we also have with this condition that this same work done that we are talking about, it can be taken from the average force times the displacement, which is the distance that is given in the first place here, which is the 35 meters, whereby the average force we are simply talking about starting from 0 in this case. So we are going to add 0 plus this value, 525, that is going to be our average force in this case. So we are going to have 525, okay, it was 525 plus 0 over 2 times what? Times S, which is our S, that is 35 meters for the whole length that we are given. Remember, we are dealing here with the whole length, which is 35 meters in this case, all right, here, the one that we are given. So meaning to say we are going to apply, or we are going to multiply this part by what? By the whole length of 35. So this part here is representing our average force in this case. This is the average force that is going to give us something like 262.5, something like that. But we are supposed to multiply now to the distance that we are given in this case. So this was going to give us the same answer of 9187.5 measured in what? In joules in this case. So that is how you can have our work done from this information. Then the other part of our question now is the power that is supplied when the end of the cable is halfway from the drum, and the velocity there is 5 meters per second. We are given the velocity in this case, and we want to calculate the power, and when it is halfway. All right, if we are given the velocity, understand that power is supposed to be taken from the force times the velocity. So we need the force when it is at a condition where it is halfway from where? From the starting point. In this case, it is halfway from the drum. So meaning to say, in this case, if we were to consider this force, our average force, we were considering the force that is in between. This is the average force that is what? Affecting our object. Now we are given that it is at a velocity of what? It is at a velocity of 5 meters per second. At a velocity of 5 meters per second. So meaning to say we are going to multiply our force to that of what? Or to the velocity of what? 5 meters per second in this case. All right. So meaning to say we are going to have our average force, which is going to be at the end power, which is 262.5 over 2 times the velocity of 5 in this case. All right, that's so. Let's check our velocity here. Our velocity of 5. All right, so we are going to multiply to our velocity being 5 in this case. So that's we are going to obtain what from this part. If you multiply, it's going to be something like 656.25. all right, which is measured in watts. All right, so let us just use our calculators and see what you're going to have at the end. So this is first part of our question 4.12. Let's check 4.1 and 4.2. Then we have got the other part now, which is 4.3, whereby we are given the construction of a part of a mass, a part with a mass of 35 kgs is lifted by a light cable through a vertical height of 30 meters in 7 seconds at a constant velocity. So here we are just given the information that is straightforward, whereby we have got the mass of the construction object that is given as 35 kgs being lifted vertically up, which means that we're talking of the gravitational acceleration considered. We're talking of the weight there. All right, so we have got the height that is being affected of 30 meters, which is our S in this case, and the time that is 7 seconds. And our question is to calculate the work done to lift the construction part. And this is happening at constant velocity. So what is going to be the work done to lift the construction? All right, remember that work done is simply force times distance. So you can work it from there. Say our work done, if it is taken as the force times the distance in this case, which is force times the height. The force that we are considering in this case is the weight of the object times the height, whereby the weight of the object we are simply referring to mass times the gravitational acceleration in this case. We have the mass of the object, the gravitational acceleration being 9,8 in this case. Then we multiply to S, which is the distance, which is the height above, which is 30 in this case. All right, so that was going to give us the work done of 1,000 and that was 10,000 actually, this one 10,000. All right, so it's going to be 10,000 and 290, which is measured in joules, which is 10 kilojoules in this case, 10,29 in kilojoules. So that is how we can play around with the information. Then on the other part, 4.32, the power required. Now we are asked to calculate the power, whereby we are simply taking the power from what? From the work done over the time taken. We have the work done in this case here, and we have the time that was taken. So simply we can calculate our power in this case, as we know that that's work done over the time taken in seconds. So the work done is 10,290 over the time in seconds, which is 7. So this was going to give us the power of 1,470, which was measured in watts, or you can write it in kilowatts if you want. That will be 1,47 in kilowatts. So the answer there at the end, it's up to you how you are going to express it when you are not given the final part. All right, then we are given the other part now to explain in your own words the term lifting machine. How do you understand the term lifting machine? What is a lifting machine? So a lifting machine, we can actually have this as a device which enables a load larger than applied effort to be raised, and that is a basic explanation that we can have there. So that's I don't know how are you going, because in your own words. All right, so here I was gonna write as a device which enables a load larger than applied force, than applied effort, in this case, applied effort to be raised. All right, so this is the condition that we can have. Then we are asked on 5.2, 2 advantages of gear trains. So gear trains, we remember they've got high efficiency. So here we can talk of things like high efficiency. We can talk of the accuracy part, the large transmission ratio. So you can talk of large transmission ratio. We've got large transmission ratio in this case. We can talk of the compact itself. It's compactable, the compact. We can talk of the positive drive. We can talk of the positive drive in this case, all right? That's okay. Let me change this one. A positive drive. Oh, okay. I clicked a lot of times. Sorry for that, guys. This thing. All right. So there we have a positive drive. So these are some of the parts that you can consider on the advantages of what? On the advantages of using the gear trains in this case. Then if you check on the other part, we are given a differential pulley in this case, which has got 12 and 13 slots respectively is in the upper block, and a load of 400 kgs requires an effort of 250 to lift it. All right, so if you had to take from this information, these slots, the smaller one, we can just write in terms of smaller s, which is 12, the bigger one, which is from the bigger diameter. So the s, this one is from the smaller diameter, 13 is from the larger diameter in this case, and we are given that the load is supposed to be of 400 kg. So here we are supposed to have our load in newtons in this case. So the load from the 400, remember it's mass times what? Gravitational acceleration. So meaning to say we have got the mass of 400 times the gravitational acceleration of 9,8. So that means our load in this case was going to be 3,920 Newton in this case. All right. So this is our load, and the effort, we are given the effort already in Newton in this case, which is 250 Newton. So there's nothing that you're going to change. All right. So this was the given information. From this information, we are asked now to calculate the following. 5.31, the displacement ratio. We're asked to calculate the displacement ratio. The displacement ratio is simply taken from our velocity ratio, which is supposed to be SE over SL. But here we are given the slots that are affected from the smaller diameter and of the bigger diameter. So we can consider from our velocity ratio concept. Remember, from our velocity ratio, we understand that, all right, let's just have it aside here. 5.31. So you can check this from our velocity ratio, which states that we are going to have 2s over s minus the smaller one for the smaller diameter, all right, which was supposed to be actually taken from SE over SL, but we are not given the distance direct. So we use the slots that we have from the bigger and the smaller. So that means our velocity ratio, which is this displacement ratio, was going to give us 2 times what? 2 times s, which is 13 over 13 minus 12 in this case. All right, so this is you and your calculator. As you can see here, this is a little bit direct from our calculator, what we're supposed to have at the end, which is 2 by 13 over 13 minus 2. 13 minus 12 in this case. All right, so this is 13 minus 12, which is going to give us a 26. So we've got a velocity ratio there, which is corresponding at what? At 26. And let's check the other part, which is the mechanical advantage. So at the same time, we are supposed to calculate the mechanical advantage. As we know, our mechanical advantage is always the load over the effort in this case. So meaning we're supposed to have 5.32 from our mechanical advantage, which is taken from the load over the effort. So we have the load in this case, but take note, it must be in newtons in this case. So from the mass that you are given, you calculated this load in newtons, which is 3,920 divided to the effort. We have the effort in this case of 250. So this one is going to give us the mechanical advantage, which is going to be 15,68. This one simply divide direct on your calculator. All right. Then if we check, the last part was to calculate what the efficiency, which is the efficiency of the whole system that we have. So from the mechanical advantage and that displacement ratio, which is our velocity ratio, remember these two, they give us the efficiency of the system in this case, which is going to be the efficiency taken from the mechanical advantage over the velocity ratio times 100%, which is the displacement ratio. So that means our efficiency was going to be the mechanical advantage of 15,68 over the velocity ratio, which is our displacement ratio of 26 times 100%. So this was going to give us the efficiency of the system to 3 decimal place. That was going to be 60,308%. That is how we could have obtained the efficiency of the system. So as you can see, this part, it's all about the formulas, and each and every graph that you're going to work with, you are supposed to know the corresponding formulas from there. Then this time we are given the information that is taken from what? From a belt drive. So in this case, we are given a belt drive concept that we have in this case. All right. So this is all right. Let's just see what you're going to have. So from our belt drive that we have, remember, we'll be having the driver and we'll be having the driven in this case. So considering here as the first part and considering this as the second part, we shall have G1, N1, and so forth. So from the first side, and also here having our slack side and our tight side. So we are given from this information the tension ratio between the what we talk about a belt drive. Then we've got the tension ratio between, which is 3:1 in this case. We've got a tension ratio. Remember, tension ratio is taken from what? From the ratio between the tight side and the slack side. So this is our T2 or T1 in this case, remember. So it is taken from this T2 as to T1. So it's like we have T1, sorry, as to T2 in this case. That is the idea of the ratio that you'll be given for what? For the size, the tension for the belt in this case, which is for the tight and the slack. All right, so 3:1. So meaning we have got the tight side T1, the slack side, which is 3:1. So remember a ratio which is written as a in this format here can be written as a fraction. If we can write it as T1, it could be written as T1 over T2 is equal to T1 corresponds to 3 and T2 it corresponds to 1. So it's play around of formulas that we have. So you're not going to waste much time. Then we've got the tension here of the slack side. We are given T2, which is 265, the diameter of the driving pulley. So remember, we said this is our driver in this case, which is the first side. So meaning to say we are given D1 from the driving pulley in this case. This is the driven part. This is the driven. In this case, this is our driver. All right. So this is the second part. So you can convert this to meters if you want. On a condition that we are going to work with meters, then we have to convert to meters. Okay, then we've got the rotational frequency of the driving pull again, meaning to say we are given N1 in this case. All right, so from this information, the question was to calculate the tight side tension of the belt. So we need to know the tight side tension of the belt. So remember, we are given that tension of the slack side, which is 265, we are given T2 in this case. So from our T2, we can be able to calculate what? We can be able to calculate our T1 in this case, which is the tight side. Remember, we are given that T2 is equivalent to 265, that is 265 Newton. So with this, we can play around our information, substitute in this fraction part, or make T2 the subject. We are going to have T1, which is the tight side, over T2, which is the slack side, in this case, is equal to 3/1. So we can cross multiply to find our T1 in this case. That is going to be what? 1 times T1, which is T1. Then here we multiply 3 times 265. So this is going to give us our T1. That was going to be 795 Newton in this case. So we have the tension that is affecting the tight side in this case, which is T1. All right, let's check the other part we are given to find. In this case, they want us to find the belt speed. So the belt speed here, we are simply talking about what? The velocity. That is the belt speed in this case. So we are referring to the velocity in this case. How are we going to obtain the velocity? Remember, velocity can be taken from pi dn. We know that the major formula for our velocity is from pi dn. All right, let me have this one. Velocity is equal to pi dn. But what you need to know, if we are given revs per minute, we can consider this as a capital letter N, like this. All right. So what we want to understand from this formula is that it is taken from either of the diameters. If you are given from D2 and D1 and N2, you can choose the ones that you are going to play with. But in this case, which diameter are we given? And which rotational frequency are we given? Rotational speed, or which is our frequency, are we given? Let us check. The diameters that we are given here, or the diameter that we have, is D1, and the rotational frequency is also for the first one, which is N1. So meaning to say, on our formula, we are going to make adjustments now to say this V here is equal to pi D1 N1. We are substituting from the first one, which is the driver in this case. So our velocity is going to be pi times the diameter in meters. Remember, velocity in meters per second. So this diameter must be in meters. So our diameter is 620 millimeters. So we are going to multiply 620 times 10 to the exponent of -3. That's our diameter times N in this case. If it is measured in revs per minute, if this is measured in revs per minute, then you are going to divide so that it becomes in revs per second, all right? So let us check here. We've got our N in revs per minute, which is 540. So we are going to divide, in this case, 540 over 60. So just divide even everything like this over 60, or just to divide the 540, you are going to obtain something like 17,53 in this case. This is being measured in what? In meters per second. So we have the velocity there. All right, then the other part was to calculate the power transmitted by the belt in kilowatts. Take note, this is not just the power, but it must be in kilowatts. So what is the idea now for the power? Remember, the power is taken from the effective force or the effective tension in this case. So we can multiply the effective tension to the velocity in this case. So power is simply the effective tension times velocity, which can be given as the effective force, that is Fe, like this. It's just one and the same thing. But where exactly are we taking this effective force or the effective tension is the difference between T1 and T2. So meaning to say our P can be given from the difference between T1 and T2, which is T1 minus T2 times the velocity. In this case, we calculated T1. Already we have our T2, so we are just going to substitute. So our power was going to be the tight side, which is 795 minus the slack side. In this case, remember our T2, the slack side was 265, even from our information here. The slack side is 265 Newtons. So you're going now to subtract these two, 265 multiplied to the velocity, the one that we calculated here. We obtained our velocity of 17,53 in meters per second. All right, so this is going to give us the power in this case. So as the question is already saying in kilowatts, so how do you convert everything to kilowatts? You multiply by 10 to the exponent of -3. The answer that you're going to have there is going to be in kilowatts. So we are going to obtain something like 9,2 0.91 in kilowatts, or you just multiply everything, then convert your result, and at the end, it's just one and the same thing. Just one and the same thing. All right, then on the other part, you are given now to calculate the rotational frequency of the driven pulley. Take note of the driven pulley with a diameter of what? Okay, of 555 millimeters. The rotational frequency of the driven pulley, meaning to say we are talking about the D2 in this case. That is from the second part here. That is, we are given the speed, the rotational speed in this case. We have the diameter, and we want to calculate the rotational speed. So the diameter there is 555 millimeters. If you are given a condition like this, you can use the millimeters, because already this is in millimeters. Okay, let's talk about the formula first. Remember, what are we supposed to calculate here is the distance in this case. I think all these other parts, they are not even important. Let's just save it aside here. All right, so if you are to take note, we want to calculate N2 in this case. This is the rotational speed. We are talking about the rotational frequency, which is N2. From the product of D1, N1, which is equal to the product of D2 and N2 in this case, we can see that if we are to calculate this N2 here, we are supposed to divide by D2 both sides. Divide by D2, we divide by D2 this part. So meaning to say at the end, our N2 was supposed to be D1 times N1 over D2. So what I'm simply saying is that if you can see these are dividing each other, so there's no need for us to change the unit, because the millimeter and the millimeter will cancel. So you can just use these units as they are for this one. There's no need for you to change. But if you change to meters, still it's one and the same thing. You're going to obtain the same answer. So remember, D1 was our diameter from what? From the driver in this case. And we have our diameter from the driver in this case, 620 millimeters, and also its speed, 540. So we have got 620 there times 540. All right, so that's 620 times 540 over D2, which is the one that we are given to say the driven, the one that is being driven has got a diameter of 555 millimeters. So we are going to use the diameter of 555. All right, so that's 555 millimeters in this case. So this is going to give us the rotational frequency of 603. So we're going to have 603,24 and so forth and so forth. So we can just, by rounding off to the nearest whole number, it's going to be 203 revs per minute, but it was supposed to be 603,243 and so on and so on. So that is how we could have calculated these values. As you can see, it's a matter of playing with the information. As we can see, the information, list down the information that you are given. You'll be given the information. From that information, list it down. By listing down the information that you have, you can find the suitable formula from there. If the information is given properly, it's easier for you to determine a formula than you are not having the information, then you want to find the formula from nowhere. So like I'm saying, please list down the formulas, the information that you're given. From there, it's going to be easier for you to calculate the any value that you are asked to calculate, or any unknown that you want to calculate. Now we have our question number 6, whereby it's on friction and hydraulics. So the first part there, we are just given to state 2 laws of friction. The laws of friction, there are so many that we can consider. So remember, if you are referring to friction, we can refer that is proportional to the normal pressure between the 2 surfaces in contact. So you can just say here friction is proportional. So let's just say is proportional to the normal pressure. So this one is to the normal pressure in this case between the contact between the two surfaces. All right, that is between the two surfaces in contact. That's in a contact in this case. All right, so that is the first part that we need to understand about our friction, and also that it is friction depends on the nature of the surface in contact also. So friction depends on the nature. So it depends on the nature of the surfaces in contact. All right, that is of the surfaces in contact. All right, so that is what we are going to have again. That is contact there. Supposed to have contact. So we just need two, but let's just add. It is also independent of the area. All right, so the friction is independent. All right, so this time is independent of the area in contact. All right, if you are dealing with the area, it is independent, okay, of the area of contact. Then also we can consider friction being independent of the speed. All right, so friction is also independent. That is independent of the speed of sliding in this case. All right, so this is what we can use as our laws of the laws of friction in this case. All right, so let us check what we have on the other part. On the other part, we are given this information is actually refers to a body that is moving on a horizontal plane. So take note, this body is moving on the horizontal plane at a constant velocity of 30 meters per second. Take note, it's at a constant velocity. Then we are given the first part of our question to calculate the coefficient of friction given the weight of the body and the frictional force. So remember, we can calculate our coefficient of friction from the frictional force over the normal reaction, which is taken as the weight, in this case, the one that is going to be opposing our normal reaction. So that's our frictional force. We have 45 over the frictional force, the frictional force 45 over the weight of the body in this case, which is 150. So that is going to give us the coefficient of friction, which is 0.3 as a decimal. Then we need the power that is being applied in this case. So how are we going to have our power? So remember that power is taken from the force. So 6.22, the power is simply force times the velocity in this case. Remember, we've got a velocity of 30 meters per second, and the force that we are going to consider is going to be the frictional force. So we're going to have 45 Newton times the velocity of what? Of 30 meters in this case. So meaning to say, we are going at the end to have 1,350 watts at the end. All right, then we are given that a container with a square base. So this is a container that we have which has got a square base, which means we are referring to a square. We are given it's a square base of 300 square millimeters. We are given its area in this case. Okay, this is a container, meaning to say we're talking about a solid. To say it's going to be something like this. Again, having another square, it's a solid that we are referring to. So we are saying the base that we are having there is a what? A square. Remember that the concept of a solid, that the volume of a solid is simply the base area times the height of that solid that you be given. So in this case, they gave us its area in this case. All right, so we have got the area there, which is a 300 square millimeters. Remember, to convert to square meters, we have to multiply by 10 to the exponent of -6. It's going to be in square meters. And also we are given the height of that container. So the height now is for the volume. So you're given the height 6 meters. If you multiply these two, you obtain the volume of what? The volume of the container. And we've got the density in this case of water, which is given as 100 kg per cubic meter. The question is to calculate the pressure exerted on the bottom of the container. What is going to be the pressure? So remember that the pressure is simply taken as a product of, all right, let's just see here. The pressure is taken as the product of density times gravitational acceleration times what? The height. That is rho GH, whereby we have the density of water given as 1000 kg per cubic meter, the gravitational acceleration of 9,8 times the height, which is given as 6. So this was going to give us the pressure, which was going to be 58,800 measured in Pascal in this case. If you want to convert to kilopascals, you divide by 1,000, which was going to be 58,8 in kilopascals in this case, or you just multiply by 10 to the exponent of -3. You are converting direct to the kilopascal in this case. Then 6.32, we need mass of the water in this case. Remember what I was talking about to say this is a square base, whereby from this square base that we have, we are having the volume from the area and the height. We have the volume in this case. So we have the volume, we have the pressure. What we want is to calculate the mass in this case. Remember, we have a relationship that can be connected between the density, in this case, between the density, not the pressure, but the density itself. From the mass in this case, we know that density is mass over the volume. If you're talking about the density, is simply the mass over the volume in this case. Even the units itself supposed to tell us here, the units kg per cubic meter is mass per volume, mass per volume in this case. And what we want in this case is to calculate what the mass in this case here. So you can simply make it the subject, since rho is equal to m over v. So that means over 1 times the mass. Mass is simply density times what? The volume. Whereby I said the volume is taken. This is from the solid, the container, which is the base area that you are going to be given of the solid in this case, which is our base area times the height of the container. We have the base area, we have the height. So meaning to say our mass was going to be the density times the area times the volume, which is area times height in this case. All right, so that is what we simply need from our information. All right, so I want to take this part. What is our density? 1000. Our density was 1000. So we're going to substitute our values in this case. That means we are going to have our mass as density of 1000 times the area times height, which is giving us this volume. So we have got the area in square meters, that is 300 times 10 to the exponent of -6 times the height of 6. So this was going to give us the area of, this was going to give us the exact mass of water in this case, which is going to be 1,8 in kilograms. All right, so that is how we were supposed to play around with our formulas. As I always say, that it's a matter of you playing around with the formulas, know your formulas, how to apply the formulas from the information that you'll be given. You are supposed to know exact formula to use. So that is how we just play around with these questions. You just have to be careful and play with the formulas and so forth. All right, on the other part, if you check the question 7, now we are given 7.1 to define the term temperature in this case. We've got the term temperature. Remember, temperature just indicates the degree of hotness and coldness of a body. All right, so this one is the indication of the degree of the degree of hotness and coldness. So here we are talking about the hotness or coldness in this case, all right, or coldness of a body. So that is the consideration that we have just 1 mark for that. Temperature measured in degrees Celsius or measured in kelvins. It's going to depend with the information that you're given. On the other part, you're given a 900 millimeter copper rod is a mass of 4 kg, a temperature of 500 degrees Celsius. The heat is immersed in a 20 liters of water until the common temperatures is given as 100 degrees Celsius. So if we are to take here, we have got the part that is affecting our copper rod and the part that is affecting from the water in this case. So this is a copper rod and it's affected to the water in this case. So from this copper rod, we are given that it is 900 millimeters, meaning to say we are given its length in this case. We've got the length of this, the length of the rod, which is given as 900 millimeters in this case. We've got its length, 900 millimeters, which is same as 900 times 10 to the exponent of -3, which is this one. Its mass being 4 kgs and temperature being 500. So we've got the mass of 4 kgs at this condition and the temperature of this copper, which is the temperature of copper being at 500 degrees Celsius in this case. All right. So at the other hand, we are now given it's being immersed in water, this copper rod. The rod is immersed in water, 20 liters of water, and the common temperature became 100. So we are given that the common temperature there, which is T2, between these two, the water and the what? The copper, that is our T2 in this case. This is the one that we are given as 100 degrees Celsius. It's not affecting water or copper. It's the final for both because the rod is now inside the water, but we are given in this case the volume of water, which is 20 liters. So what are we supposed to do with the volume? Change it to kgs. Remember, a liter is equal to a kg. So meaning to say this is simply equal to 20 kgs. We are given the mass in this case of what? Of 20 kgs from what? From the volume that we are given. We are going to convert it to a mass. So we have the mass of water. All right, so let us check the first part of our question. We are given that calculate the heat that is going to be transferred to the water in this case. If 20% of heat is lost to the atmosphere, take note, 20% of heat is lost to the atmosphere. In actual sense, we were supposed to have this as the heat that is affecting the copper in this case is supposed to be as the heat that is affecting our water in this case. But in this case, it's no longer be like that because they are saying 20% was lost to the atmosphere. So what we can do is to calculate the heat from the copper that was immersed in water. Remembering that the heat, all right, so that's 72.1. We are going to calculate the heat for copper. In this case, remember, heat is the mass times the specific heat capacity of copper times the change in temperature. In this case, we're supposed to have the change in temperature, which is the temperature of copper minus the final temperature T2 in this case. So out of this, that is where we are going to take the one that was transferred to the water. All right, so let us have our mass times the specific heat capacity of water, of copper. In this case, we're talking about the specific heat capacity of water, of copper in this case. All right, sorry for this. The one for copper, we have this from our information sheet on the first page, that was 390 times T copper minus the final temperature, the temperature for copper being 500 minus 100 in this case. All right, so this was going to give us something like 624,000 measured in joules in this case, which is something like 624 kilojoules in this case. But they are saying 20% of this heat is being lost to the atmosphere. So meaning to say it did not reach the water. The 20% did not reach the water. So out of the 20%, we are going to subtract now the one that we lost, and we are remaining with 80%. So the 80% is the one that is affecting the water. So this is the one that is going to affect the water in this case. So meaning to say the heat that is going to be transferred to water in this case is going to be the 80%, which is 80 over 100 times the total heat that the copper rod was having, which is of 624,000 joules or 624 kilojoules. Like I said, this is same as 624 kilojoules in this case. All right. So if you are to express this already in kilojoules, you're going to obtain your answer as it is going to be 499.2 in kilojoules in this case. All right. So that was the idea of our question. We now have the heat that was transferred to the water in this case. And from there, they are now asking us now to calculate the original temperature of the water in this case. Remember, for the water, what we only have here is the mass and the final temperature for both, because this final temperature is affecting both the water and the copper rod in this case. So if we are to take note, now we have the heat that was transferred to water in this case from the 80% that we took from the copper. We transferred 499.2 kilojoules. This is the heat that is affecting our water. So from our question, we want to calculate the original temperature of water, which is the temperature of water. How can we do so? We can simply take it from the heat that is taken from water. Remember, the heat from water is going to be, again, the mass times the specific heat capacity of water times the change in temperature in this case. But this change in temperature this time, it must be the heat from the final, because when this rod is immersed, it increases the temperature of water. So it means we are going to have T2 minus the temperature of water, which is the original temperature that we are supposed to calculate. So in this case, we have everything. In this case, we can just substitute the heat for water, the one that was transferred being 499.2 times 10 to the exponent of 3 is the mass. Remember, the mass from the volume, we said the mass is going to be 20 there, times the specific heat capacity from our information sheet for water. It's 4187 times T2 minus T water, T2 being the temperature for both water and copper combined. So we are going to subtract the temperature for water from there. So that's, we can calculate our T water in this case, okay? So here, without wasting much time, just divide by this on the other side, because we want to remain with this part. So we are going to have 499.2 times 10 to the exponent of 3 over divide by the whole of this part here, which is 20 times 4187. So here we are going to remain with the 100 minus the temperature for water, which if you divide these two, you are going to obtain 5,961 is equal to 100 minus the temperature for water. So to find the temperature for water, you can transpose it to the other side so that it becomes a positive. So it's going to be 100 minus, we transpose this one to the other side, which is going to be 5,961. All right, so this is going to give us the temperature that is affecting the water in this case, which was going to be 94.039 in degrees Celsius. All right, so that is how they wanted you to play around, change of subject from your mathematics, how to solve an equation. They want you to apply your mathematical skills there to solve for these typical equations like this. All right, then on the other part, we are now given 7.23 now, the change in length. So this one is no longer about the heat or so forth. You're now talking about expansion that can happen in this case. So this information is not actually necessary. So the change in length in this case, we understand that it can be taken, the change in length from the linear coefficient of expansion times the original length times the change in temperature in this case. So we're talking about the change in length of the copper rod. So we are going to take the linear coefficient of expansion of the copper rod, which we are given also from our information sheet it's given as 0,00, that's 0.17, all right, times the original length now of the copper. The original length is the one that we have. The length of copper originally is what? 900 millimeters. So if you use the millimeters, your change in length is going to be in millimeters, all right? Then the change in temperature, I talked about this. This one is the temperature for copper minus the temperature T2. In this case, we have the temperature for copper here, which was 500, T2, which was 100. So you simply have to subtract. That's 500 minus what? Minus 100 in this case. All right, so that is going to give us the change in length, which was going to be 6.12 millimeters. So this question was simply taken from our expansion in this case. All right, so that was it. Question 7.3, we are asked to name, in this case, 3 types of fuel and give an example of each from each fuel that we have. So these are the states of how fuels can be obtained. We can have this in solids, whereby we give examples such as wood, coal in this case. We can have these fuels in liquids in this case, where we are talking about things like petrol, diesel in this case. We can talk of oil in this case, so many that we can have there. We can have it in form of a gaseous state, which is gas. We can talk of butane, we can talk of methane, we can talk of propane. In this case, we're talking about the gases that can be found in the examples in this case, that is examples of our gaseous state that we can have. All right, then on the other part, we are given question 8. So this was a scanned paper, that's why it was like this. I was just someone sent on WhatsApp, but it's fine. I think it's clear. Let's see. Question 8, the particle structure of matter, asked on 8.1 to define the atomic the number of an atom. Okay, the atomic number of an atom in this case. So it's simply the one that's the number of protons in the nucleus of what? Of an atom. That's it. All right. So this one is simply the number. So is simply the number of protons, in the nucleus, all right? In the nucleus, all right, of an atom in this case. So that is the atomic number there. Then name 3 fundamental components of an atom and state how each one is charged in this case. So there we are talking of the protons, which are positively charged. So we are talking about being of positive charge in this case. We talk of the electrons. In this case, we are going to refer the electrons, which is of negative charge. These ones are of negative charge. We take of the neutrons in this case. So these ones, they are neutral in this case, so they do not have a charge. So there is no charge in this case because they are neutral. All right, so these are some of the components that we are being asked in this case. All right, so let's move on to the other parts. 8.3, we were given to choose the correct option from given brackets and write only the answer that you're given, in 8.3 and so forth. So pure water is what of electricity? Is it an insulator or a conductor in this case? So if you talk of pure water in this case, it's referred to as an insulator. Though the one that we apply, that we use, don't play around with it, but pure water is actually an insulator. All right. 8.3, name 3 methods of preventing corrosion. If you're talking about corrosion, you can prevent this by painting. All right, so remember, you can have this by painting, by oiling, by applying oil. Okay, by applying oil or by oiling in this case. All right, let's just say by oiling or greasing, because it's just one and the same thing. By oiling or greasing in this case. So this can actually reduce the corrosion to happen, or by electroplating with zinc. All right, you can also reduce by electroplating with zinc in this case. So there's so many parts that we can actually consider or that we can have, just have to play around with them. All right, on question 9, we are given on electricity, but the first part was to convert 28 micro ohm meter. In this case, we are given the micro ohm meter, convert it to the ohm meter in this case. All right, so remember that micro simply means times 10 to the exponent of -6. So that's 28 times 10 to the exponent of -6. So as a decimal, it was going to be something like 0.00028. We have -6. So if you consider, we've got 1, 2, 3, 4, 5, 6, which is 28 there. All right, so it was going to be 0. This micro ohm meter in this case. So the micro there is the one that we used, times 10 to the exponent of what? -6. Indicate whether the following statement is true or false by writing only true or false. All right, so given that porcelain is a good conductor of electricity. All right, that one does not conduct electricity. It's an insulator, so this is false. Then we are given a voltmeter is connected in parallel with a device to measure its voltage, which is true. An ammeter is connected in a series if you want to measure current, a voltmeter in parallel, which is actually true from that statement that you are given. Then we are given now on 9.3, 3 resistors, the 2 ohm, the 4 ohm, the 9 ohm are connected in parallel. So in terms of our combination, remember in parallel, guys, it's just something like this. We are just having something like this in parallel. So we've got these 3 resistors, then later on connected in series to another resistor like this. We are now having our the 3rd resistor connected in what? Connected in series. So definitely it is going to be connected in series to a voltmeter. You're going to have a voltmeter. So these 3 resistors, we've got the 2 ohm, the 4 ohm, and the 9 ohm resistor here. So we are going to have the 2 ohm. So that was the 2 ohm, the 4 ohm, and the other one is the 9 ohm. So it is this whole combination. They are saying it's connected to a 16 ohm resistor. In this case, the whole of the parallel combination is then connected to the 16 ohm resistor here. So this is where we have our 16 ohm resistor. So our question was calculate 9.31, the total resistance of the parallel connection. They are just working with this part in parallel. Calculate the total resistance of that parallel combination. So how do you calculate the total resistance in a parallel combination? There are 3 resistors that we are talking about. So it's difficult for us to use product over. Yes, you can use product over sum for the first 2. You use again product over sum, but to avoid that, we can use the formula for a parallel combination. 1 over Rp is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So you're saying it's 1 over R1, which is 2, plus 1 over R2, which is 4, plus 1 over 9 in this case. All right. So that's 1 over Rp is going to give us. So here we are supposed to apply or use our calculator properly. I want to explain this part here. Let me have my calculator so that I explain properly how we are going to have the answer at the end. So it's 1 over 2 plus 1 over 4. All right, plus we are going to add 1 over 9 in this case. So that's 1 over 9. So this is going to give us 31 over 36. So this is 31 over 36. But what we need here is to find this Rp here. So how are we going to find Rp? We simply invert this. To invert means the inverse of 1 over this means the inverse. That means we simply introduce 1 over on this side. You just divide 1 over this part from your calculator. So meaning to say here, we are just going to say 1 divided by the answer that we had, which is going to give us 36 over 31, which is as a decimal, that is going to be 1,161. So we're going to have 1,161 in ohms. So that was the total resistance that we're going to have in a parallel combination. Remember the formula for a parallel combination. Then now they want the total resistance of the 4 resistors. Remember the parallel combination was for the 3 resistors. Now for the 4, we are considering this one in series. So we are now calculating the total resistance, whereby we simply have to add in this case. All right, so that's 9.32. So our total resistance is going to be the parallel combination and the resistor that is in series, which is the 16 ohm resistor in this case. So we obtained in our parallel combination, we obtained 1,161 plus the series resistor that we have here, which is 16 ohms. So that was going to give us 17,161 in ohms as our total resistance in this case. All right, so that was application of this question, I think, from there. So let us check the other part now, which is for 9.4. 9.4, we are given that here, calculate the length of a copper wire having a diameter. In this case, we are given the diameter of the copper wire of 7 millimeters, resistance of 3 ohms, and at a temperature of 20 degrees, all right, Celsius. So how can we calculate the length? Remember from our resistance that resistance can be taken as resistivity times length over area in this case. So what we want here is to calculate this length that we are given here. So we can make it the subject of the formula. Let's see, we cross multiply. That is going to be this one times resistivity times length. Then we have got resistance times area. As we want to calculate the length, so you can make the resistivity the subject there by dividing by the resistivity. Length is going to be divide by resistivity here, divide by resistivity is going to be RA over the resistivity. So if we are to consider, remember our area is taken from what? From pi d squared over 4. That is our area in this case. And we have this, the diameter should be in meters. So this is same as 7 times 10 to the exponent of -3 in what? In meters. So we can just substitute also the resistivity of copper. If you check from information sheet, we have got the resistivity of copper they gave us at 20 degrees Celsius. So that is the one that you're going to simply substitute. So our length is going to be the resistance, which is our resistance in this case is 3 ohms. So we have got the resistance of 3 ohms times area. Remember, it's pi d squared over 4. So it's going to be pi times our diameter in meters. Now it's 7 times 10 to the exponent of -3. So we are going to have 7 times 10 to the exponent of -3 squared over what? Over 4. So this is for the area, everything over our resistivity in this case, which is the one for what? For copper at 20 degrees Celsius. And this is given, like I said, from our information part, is given as 0,000018. All right, that's 0.18 like this. All right, so here please make sure that you use your calculator on this part. Use your calculator properly. You are going to obtain since we converted this to meters. If you wanted, we're just going to use millimeters, but since we converted to meters, meaning to say this length is going to be found in meters, you're going to obtain something like 6,414,085, which is in meters. So to convert back to millimeters, you just multiply by 10 to the exponent of -3. You divide in this case to convert to millimeter, or just leave it like that in meters as it is, still one and the same thing. All right, then we are given to state advantages of electromagnetic induction. For electromagnetic induction, it is actually cheap. So this one is cheap. It's actually simple to work with. It's actually reliable. So these all are advantages. It's controllable. All right, it's actually controllable, and also it's efficient. So we can have this part on our conclusion. So that was just 3 marks. We just need 3 advantages. They were supposed to take 3 from the information that we are given. So as you can see, guys, that was the full paper. That was what we're supposed to have to in a total of 100. So let us communicate in the comment section. Let us see if there are any mistakes that happened there, you know, dealing with these technology things, when you are writing this and that can make errors, this and that. So let us know. Let us know so that we can play around again with that question to correct if there is any part that we see. But for now, that's it, guys. Till we meet again.